Okay, my name is Jesper Ortiz. In this practice, I miss recording something that I cared because of poor organization with my team. But anyway, I'll explain all the activities we did. Next, I'll show a video, and while it's playing, I'll explain the activities done in this practice. Okay, as this is this video. Okay, uh, Step 1. Oscilloscope power up and installing connection. The oscilloscope was powered on and the probes were connected to channel CC1, ensuring correct polarity when connecting them to the oscilloscope's test point. Step 2. Signal observation and signal calibration. After connection, the signal was observed the screen, recording the initial peak-to-peak voltage VPP and frequency in hertz values. The oscilloscope was then calibrated using the fault or offset function. After calibration, the VPP and frequency values were verified again with no significant change observed, indicating a correct initial calibration of the equipment. Step 3. Explanation of oscilloscope option. A review of the most relevant oscilloscope option was conducted, including the calibration procedure and the function available in the measurement menu. This section was based on prior theoretical research. Step 4. Detailed analysis of oscilloscope menu. A deeper analysis of the oscilloscope menu was performed exploring the options in the measure, arc-wheel, display, cursor, and utility menu. The key functions of each are described below. Measure menu. After automatic measurement such as BP or MEC, voltage, frequency, period, pulse width, and duty cycle facilitate signal analysis. Is this a little this time? Step 5. Function generator connection and signal variation. The positive probe of the oscilloscope CC1 was connected to the output of the function generator and the ground of the oscilloscope to the ground of the generator. The generator was adjusted to produce a sine wave with an amplitude of 5 bpp and frequency of 1 kHz. The sine wave was observed on the oscilloscope. The amplitude and frequency were varied in the generator, observing the following effects. Amplitude. Decreasing the amplitude caused the height of the wave on the oscilloscope to increase proportionally. Frequency in frequency. Increasing the frequency caused the wave to compress horizontally, showing more cycles in the same amount of time. Step 6. The signal from the generator was changed to triangular wave. The triangular shape was observed in the oscilloscope. The amplitude and frequency on the triangular wave were varied, noting the same effects as with the sine wave. Amplitude affected height of the triangle, and frequency affected the number of triangles visible the screen. The process was repeated with the square wave. This wave in the oscilloscope was displayed as a series of square pulses being displayed, changing of the height of the pulses and varying the frequency to the number of pulses in the screen. Step 7. Signal rate. Finally, the signal observed in the oscilloscope was rate. The values of VPP, frequency, and period were not for each type of sine, triangular, and square. These data were used to draw the corresponding waveforms in a dry diagram. Conclusion: Dillard provides a practical expression and describes the oscilloscope and a function generator to analysis and manipulate various waveforms. The effects of amplitude and frequency change on different signal types were directly observed and documented, reinforcing the theoretical understanding of this fundamental concept in logic. This is all for today.